Now let's try and develop the expression for line integral for work done. Now let's try and first begin with the understanding of work done in physics. Then we'll come back to this situation where we'll develop line integral for displacement along any general curve, right? So how do we actually define the work done? Work done is given by the scalar product of force and displacement. So I'm talking about elemental displacement, but if I say that I can generalize this for a straight line situation instead of a curve, what I can do, I can redefine my work done as F dot S, where S becomes my displacement vector and F is my force vector. Assuming both of them are constants, then this definition will give you the work done. For example, if I talk about the displacement along the x-axis by applying a force which makes an angle 45 degree to the x-axis, then what happens, it is as good as saying that you are trying to pull an object by applying a force at 45 degrees. And what happens, what is the component of the force that displaces a particular entity, a mass, along this x-axis? It is the component of force which is F cos 45 degrees. And if I displace that particular mass by, let's say, a distance, let us say x, then F cos 45 simply multiplied by x, this is basic multiplication, will give you work done. So in other words, if you want to state in this form, what happens, it is F dotted with S, dotted with S will give me the work done. How do you actually re-represent this in the vectorial form? Because F is inclined to the x-axis, it is also inclined to the y-axis, and therefore F has got two components, one along the ith direction, F cos 45 in the ith direction, and along y-axis it has got F cos F sin 45, just to generalize, along the jth direction. When this is dotted with the displacement which is purely along the x-axis, that is I into x, okay? When it is dotted, I will simply get Fx cos 45 degree. So this is what we mean. So unless along the direction of displacement there is a force, you are doing no work whatsoever. That is the whole philosophy. Now can we apply this to a general situation, and why integration becomes warranted? Because your S can be a curve whose which is characterized as a function of x and y. F also could be a function of x and y. When these quantities become variables, what happens? You cannot generalize or apply a rule like this. You will have to first find the elemental work done, that is by applying force across a small length of the curve and then integrating it across the length of the curve, you will be able to produce work done. Only for nonlinear situations, integration or calculus becomes warranted, and here we are seeking work done by displacing along a curve. Otherwise, if you are displacing everything along a straight line, the integration will be required only if the force is varying. If the force is constant and your displacement is along fixed straight line directions, then no integration is required. So let's try and find out the general expression. Now let's say that I'm in the xy plane, that is yx. I'm trying to displace a particular mass along this particular path, right? That is from x1 y1, x2 y2, and all along the path my force is varying. That means if I am defining a force F1 which is function of x comma y along the ith direction, and if I am defining a force F2 function of x comma y along jth direction, what happens? The magnitude of the force at every point, because it's a function of x and y, and since x and y continuously varying across this curve, what is happening is varying. So therefore integration automatically becomes warranted. So now, how do you actually go about doing that? As you have done at the +2 level, whenever you want to integrate an area or a volume, what you do, you first consider the elemental area or elemental volume, then integrate to find the total volume. Here also, first we are going to find the elemental work done, and then when you integrate, you will get the total work done. So now let's consider a very, very small portion of the curve arbitrarily at any point, so that I can first develop an expression for work done across that particular length, and then carry out the integration to find the total work done. So if I write the equivalent displacement, it is this displacement, because I can afford to approximate this particular small infinitesimally small curve length by a straight line, because when you consider a very, very small curve length, the secant of that becomes equal to the curve length. What I mean is, here of course we are exaggerating for your visualization. As the curve length becomes smaller and smaller, what happens? The secant becomes equal to the curve length. Of course, for exaggeration we have drawn a much bigger length. This is infinitesimally small length, right? So what happens? You can see that as I draw smaller and smaller secants, that is, the curve length I am covering is also becoming smaller, and that at one point becomes almost equal to the secant. So therefore, this is my displacement, and this displacement can be vector sum of two more vectors. See, I am getting myself displaced from A to B. I can also go along the path A to C and C to B. So this becomes my equivalent displacement. So I am getting displaced from A to C and then from C to B, but the vector sum of these two displacements is AB. So therefore, my displacement from A to B is equivalent to my displacement along AC plus my displacement along BC. So therefore, I can write this as F dotted with S, okay, F dotted with the ds vector is equivalent to saying, I would put in the definition of ds here. What is the definition of ds? If I call this dx dy, which is of course true for the Cartesian space, so what I get here is dxi plus dyj, and then if I take the dot product, then what happens? I will have to re-represent f in terms of the components, otherwise I cannot take the dot product. F1 x comma yi plus f2 x comma yj, and then that is going to be dotted with dxi plus dyj, right? If I did the dot product, what I will get? I'll get f1 into dx and f2 into dy. That becomes my work done for the elemental displacement. But for the total displacement, what should I do? I should integrate. Let me come to that. So in order to get my total work, I will have to integrate f1 into dx plus f2 into dy. This is quite easily doable, because you have got the definition of force in terms of x and y, definition of force that is F2 in terms of x and y. So you can integrate with respect to dy, integrate with respect to dx, and finish it off. But now the challenge arises. Now we are displacing along, you can see we are displacing along a certain curve. We are not displacing along a general straight line, but we are displacing along a specific curve. So how do you actually integrate this? Now if I write the definition of the force, it is obviously in terms of x comma y, and here also it is in terms of x comma y. Now observe one thing very carefully. I can give any arbitrary definition for f1. Let us say I am talking about xy plus y cube. Okay, just a definition I want to fit in, and here let me say it is y square x plus x square y. Now how do you integrate a y term with respect to x here. How do you integrate an x term with respect to y here? Because y square x cannot be integrated, because your integration is with respect to y, because you are finding work done for displacement along y direction, and you are trying to find work done for displacement along x direction. How do you do it? Now here you are going to utilize the definition of the curve. Suppose you say x is equal to, let us say, y is equal to x square is the definition of the parabola along with which I am displacing. Now my job becomes easy, because my force is defined in terms of x and y. At every x and y it is changing, but it is changing in such a way that y becomes equal to x square, because your displacement is along that particular curve. So what I would do here, I would simply replace y by x square and y cube by x square, that is x power 6. So that becomes easily integrated. And here also I'm going to replace x by y definition. That means x becomes root y and x square simply becomes y here, and that can be integrated quite easily. So that means if you want to find work done along a specific curve, and also your force definition is in terms of x and y, and force definition is also in terms of x and y, then this becomes warranted. Otherwise it becomes very simple. If you say that my force is not varying, it is constant, then force into displacement, that is F1 into displacement and F2 into displacement, simply gives you the work done. That means if I have to make it very, very clear, if I choose this particular curve definition, if my force along x is constant, so then what happens? I'm only concerned about my x displacement, let us call it x naught, and then multiply that by force. And if I say that this is my y displacement, then y displacement into force will simply give me the work done, because I'm moving from x1 y1 to x2 y2, where x2 minus x1 is x naught, y2 minus y1 is y naught, which can be your integral limits here. Because if I replace f1 by a constant, and if I put my limits to be x1 to x2, what I will get on integration, I will get the difference of x2 minus x1, which is x naught into f1. If I replace this by my limits y1 to y2, the difference of y1 and y2 is nothing but y naught. If f2 is a constant, I'll simply get my work done. But if you are displacing along this particular curve, and if your force is not constant, function of x and y, then you will be forced to express them, that is either x in y in terms of x for integration here, and here x in terms of y using this curve definition. That's very important. And therefore, if I generalize, I can always write this line integral along a particular curve as f dotted with dr, where I can say dr is simply dxi plus dyj. Of course, if you have a three-dimensional situation, then it is dzk, and f can also be written as f1i function of xyz, f2j function of xyz, f3k function of xyz. If otherwise, if they are constants, simply the displacement, actual displacement multiplied by force will give you the work done. So this is how you interpret and look at this particular expression. So let me walk you through what exactly we did. We started with the idea of work done, which is nothing but the scalar or the dot product of force and displacement. We made it very, very clear that unless force has a component along displacement, the work done is 0. And I give you the example of this force, which can be represented as f cos 45, the ith component, f sin 45 as the jth component. Since the displacement is along x-axis, it is just the ith component, which will give you the work done, which is f dot s. But if you are displacing along a curve, you cannot generalize, so you will have to calculate the elemental work, which is f dot ds. But ds you can see that is the equivalent displacement ds if you consider, and the equivalent displacement if you consider, it is dxi plus dyj, and that is what exactly we have brought over here, and that multiplied by f1 dotted with f1, that is scalar multiplication with f, will give you f1 xy y and f2 xy j, because you are taking the dot product with f. F has this particular definition. If I plug in the definition of f, I will get this as the work done. But what is to be noted here is that you get two integrals, f1 dx and f2 dy, because you are just taking the dot product here. When you take the dot product, the ith components multiply, give you one integral. The jth components multiply to give you the second integral. But what is to be noted here is that since you are displacing from x1 to x2, y1 to y2, you will have to integrate f1 with respect to x and f2 with respect to y. What happens to the integration? It becomes challenging, because if you are saying that f1 is a function of xy, f2 is also a function of xy, I have taken an arbitrary definition here for you to visualize what is going on. You cannot integrate this because there is a y term. Here you cannot integrate, but there is a x term. Unless you have pure x terms, pure y terms, this integration is not possible. But since the displacement is along a parabola, I just supposed it to be y equal to x square as an example. Then what happens? My force definitions along this curve change, because my force value depends on the coordinates of the curve on which you are displacing. It depends on the coordinates, because it's a variable force defined in terms of x and y. Since you are moving along this particular path, at every point what happens, there must be a component of the force that can be split along x and along y, and that is where these integrals get defined. And since that to happen, at every point the force must actually tread the definition of this particular curve. That means your x and y in the force definition must be expressed using this relationship. And once you do that, you will be able to integrate, because you will have pure x terms and you will have pure y terms. Then these two can be integrated. So therefore, if you want a general definition, then it is f dot r along the curve, where dr is dx, dy, dz, and this is the f force definition, because when you take the dot product, f1 dx you will get one integral, f2 dy you will get another integral, f3 dz you will get another integral. So therefore, this is how the line integral is conceived for work done along a curve. Let's move on and look at more discussions. Well, engineering and math are absolutely inseparable. We interventions day in and day out try our level best to make math as simple as possible and also of great practical value to every aspiring engineer. Do you want us to reach the masses? Please like us, share and subscribe. Do not forget to turn on the bell icon.